Hello. Okay. So welcome everybody to my talk about our concept for a fluid independent thermal gas flow sensor. I'm Christof. I'm working at TrueDyne Sensors. We have a booth right there in the entrance with IST. Together with IST, we are in the same booth. So this talk is about cooperation of sensors from IST and TrueDyne. So TrueDyne Sensors, what do? We are mainly manufacturing MEMS-based density and viscosity sensors for gases and liquids. So that's our main focus. These are two examples of gas density sensors we have. So they basically all have a resonating element, and by measuring the natural frequency of this resonator, we can somehow deduce the density of the gas which is in contact with this resonator. That's the basic concept. We mainly use this for concentration measurement of gases in applications. Sorry, it's a bit strange, this microphone. Do you hear me? Good. So, concentration of binary mixtures, for example, for protective gases, or in the food industry, if they have a mixture of nitrogen and CO2, or for welding protection gases, and so on. So that's kind of our sensor portfolio. You will see it at the booth. So we have different sensors for different applications, measuring liquid or gases, density, viscosity, and of course also flow. And the talk today will be about flow. So, fluid independent thermal gas flow sensor. What's the challenge? A calorimetric flow sensor typically needs to be tuned to a specific gas. So the calibration is different if you use another gas. So the solution, our solution, is to combine this thermal gas flow sensor with one of our density sensors. So by measuring the density of the gas, we can deduce if it's which gas it is. When we have a list of 10 gases with the density, we can detect which gas it is. Or if you have a mixture of two gases, typically we can say what's the concentration, and the concentration can also vary, so we can correct for that. So the primary sensing element is a silicon gas flow chip from IST, and the secondary sensing element, the density, is a tuning fork, a quartz tuning fork, typically used in watches. So we are a Swiss company, we use a Swatch tuning fork. Open the cave and let the gas be in contact with the resonator, so we can measure the density. So it's somehow like the Swiss Army knife. It's multiple options in one tool. So we combine multiple functions in one tool. So let's see the sensor in detail. So we have demonstrator on the booth. We can show you there how it works. So here you see how we manufacture that. So we have a PCB, and one side this thermal flow sensor, on the other side this tiny sensor here is the quartz oscillator, and then we have a pressure sensor, since density is useless if you don't know the pressure and the temperature. And then this PCB is flipped to a manifold where we have a flow channel where the thermal flow sensor is in contact. Then we have a chamber here where we measure density, and then we have a bypass, an optional bypass channel to adjust the flow range to a certain application. Our channel is 1.1 times 1 millimeters for the flow channel. The bypass can be variant. Then we have a PCB which combines all this, calculates the model, which I will show you right now. So that's again the concept. We have this resonator, which has an output natural frequency. Then we have the temperature and pressure from the sensor, pressure sensor. Then we go to a model, we calibrate this sensor for density. So I will show you the calibration right afterward. Then the sensor outputs density, or you can calculate it to reference density, density at reference conditions, or concentration of mixtures. So we can have a clean gas detection, as I already told, or a binary mixture, the concentration of a binary mixture. The other path is this thermal flow sensor, which has a heater, a central heater, and two thermopiles, and so the delta temperature difference of these two thermal sensor is somehow proportional signal to the flow. And by knowing the gases, we can correct in time. Just if the gas mixture changes, we can correct the calibration values. So let's see how the density sensor performs. So these are different gases: argon, nitrogen, CO2, helium, at different pressures. And you see, as lower the density, the higher the frequency. So in these watch tuning forks are tuned to 32.7 kilohertz at vacuum. So helium at low pressure is nearly vacuum. And if you increase the pressure and the density and use heavier gases like CO2, the frequency goes down, so you can measure density. That's typical calibration of what we do in our company. So we have different gases at different temperatures, like 0 to 60 degrees, or even minus 10 to 60 to 70 degrees. Then pressures from atmospheric up to 10 bars. So that's a typical calibration procedure. So we can measure density, and these are different density or reference density at reference conditions of different gases. So you see, pure gases you can distinguish. So not every gas is easy to distinguish over density, but in most applications you are able to clearly distinguish two gases over density. Or if you have a binary concentration of two gases which have a different density, over the density you can calculate the concentration. Then we have the thermal flow sensor, which is a silicon-based sensor with a central heating element and two thermopile temperature sensor. It's typically symmetrically arranged, but what is important here, the sensor is not completely symmetrical. I will show you later the output of that. This heater is not symmetrically arranged on the silicon. So how this thermal flow sensor works, you have this. You can operate the thermal flow sensor in different modes: constant heating power or constant heater temperature. We use constant heating power, and then we look at the temperature difference. That's the best way to work with this sensor with low flow rates. So a typical flow output looks like this. The voltage output is somehow proportional to the temperature difference, and as you increase the flow rate, the temperature difference increases, comes to a maximum, that goes back. So typically you would measure in the first slope when the temperature rises. So that's a signal how it looks for our sensor. So if you increase the flow, the temperature will difference will increase and comes to a maximum at a certain point. So typically, if you zoom, we use only this first slope to measure, where we have a nearly linear signal. It's not completely linear, but we can calibrate this nicely out. And that would be a typical calibration with nitrogen. Now comes the problem of the thermal sensor. If you use other gases, this sensor output is completely different. So if you use CO2, you get a higher output because more mass flow will come to this sensor, and the signal is somehow proportional to the mass flow. If you have a lighter gas, you have lower flow, signal output. What you see in this picture is also at zero flow, you have different levels of the sensor output. This is due to this asymmetric, it's not completely symmetric sensor. So you have a slight temperature difference even at no flow. That's so-called the 0 point. And if you plot this 0 point for different gases against thermal conductivity, you see it's somehow dependent on the thermal conductivity of the gases. So you have to know the thermal conductivity of your gas to correct for this 0 point effect, which it's not much, but at low flow rates it can be an issue. So that's a reason more to know exactly what your gas is in the mixture. So let's see how it works in practice. So we have a calibration with, now we have a 0 point corrected raw value of the sensor plotted against mass flow, because it's basically mass flow which is the main importance of the output, delta T output. And if you look at the theoretical considerations, so you have this heat conduction equation, and if you plot mass flow, you see it's somehow dependent. That's the heating power. You have temperature difference, and then there is this factor thermal conductivity divided by heat capacity, which is somehow the gas conversion factor which you have to correct for the gas. In reality, it's more complex. You see, there is more parameters here because we have a small membrane, and we have only a small part of the gas is really in contact with our sensor. So viscosity of the gas and so on will also play a role, but the main factor is this thermal conductivity and CP, which you have to correct. And so here you see this theoretically conversion factor, and here is the measured conversion factor. You see for helium, for nitrogen and air, it fits perfect. For argon, it's not quite the same. For CO2 as well. So it depends on your manifold flow conditions on your specific sensor. So you have to calibrate it once for your type of manifold and sensor arrangement, but then you can store it in your sensor brain and then measure density, choose which gas is it, and then correct for thermal conductivity. You know the 0 point effect, and you know the correction factor, and this can be done automatically. If you say it's one of these gases, you're sure the sensor chooses which gas is most probable and then corrects for that. This works for clean gas detection quite well, and here you see a typical sensor output. We can measure within 2.5% roughly of the max flow, all these different gases. So go a bit further, does it work for binary mixture as well? So if you know which two gases you have, typically in industrial application, you know these are these two gases, but you don't know the mixture, and the mixture can change. So by measuring density, you see these are some examples: nitrogen, CO2, nitrogen, helium, methane, hydrogen, and you see the density changes nicely linear with concentration. So by measuring density, you know the concentration of your binary mixture. So for an easy mixture like, for example, CO2 and nitrogen, you see what would be an output of a standard sensor. So without correction. So this sensor is calibrated with nitrogen. So the mass flow controller says is set to 100 or to 50 cubic centimeters per minute. The sensor measures quite correct at 5% CO2, but as higher the CO2 concentration is, the wronger is the output. And here the main effect is the density of difference from CO2 to nitrogen. In our sensor concept, we can correct it for every concentration in time. So we can correct the slope easily. But this is a nice behavior. CO2 and nitrogen are quite linear mixed. It's not always like that. And I try to explain that the main factors are thermal conductivity and heat capacity, which change this thermal conversation factor. And for nitrogen CO2, they behave quite linear, but for nitrogen helium or methane hydrogen, it's even not linear at all. So you see it's some big unlinearities in your mixtures. So what you have to do is to really calibrate this once, measure it once for this mixture, and then store it in the sensor. And if you know the concentration, you follow this curve and can adjust the conversation factor for these mixtures. So, and again, if you do this, for all these mixtures, you get a quite linear output, which is automatically corrected for all concentration. So what are applications that we can imagine or where we use this sensor concept? So I already told this modified atmospheric packaging for salad or meat. It's hard to find a sensor which exactly measures the concentration of these gases. That we can do with density. And if you have also the control flow, you can, of a varying mixture of CO2 and nitrogen, you can use this sensor combined with the flow sensor as well. Another application would be hydrogen fuel cell, where you have to measure a hydrogen and nitrogen mixture, which can vary. And you can monitor it over density, the concentration, and correct the flow sensor. Then you have also the corrected flow value of this variable mixture of hydrogen and nitrogen. Another application is welding gas monitoring, where you have a combination typically of maybe argon and hydrogen or CO2 as a protection gas, or helium. And so you can detect if the mixture is correct, can correct the value. You can even say if the gas bottle is the wrong gas bottle or not. So the sensor tells you which gas he recognizes. And that's somehow the clean gas monitoring, which we also use mainly medical and chemical pharmaceutical application. It's important to have high nitrogen or non-nitrogen, oxygen, and the sensor can detect if the right gas is on, the right bottle is there and correct for that as well. And then one application we also tried, and we have some customer which wants to implement this, is the fermentation monitoring of beer, for example, here. So you have a tank with which ferments, and for every sugar molecule which is converted to ethanol, CO2 molecules are produced, and if you measure the output of this tank over a week, and sum the mass of CO2, you see the CO2 increases, and you can calculate the alcohol content which you must have in your beer. So we can monitor the fermentation. So I come to my conclusion. So we have demonstrated a way to come to a low-cost thermal flow sensor which is independent from gas composition. So it can detect clean gases quite well from a list of clean gases you give him, or you can choose binary mixtures. You have to say, I have a binary mixture of these two gases, and he can correct automatically the output. What we will focus in future is to measure more complex mixtures, so we need more sensor signals to distinguish 3 gases or 4 gases in a varying system. And if you are interested to visit us, you find us at the booth 308 with IST, and you see this sensor where you find these balloons, where we show that if you use the wrong correction, the balloon is not the same, has not the same size than the other one with the right correction. So happy to answer some questions, and visit us on the booth if you want to know more about the sensor. Yes? Sorry? The density, the temperature we also measure for the density. We measure temperature and pressure and have to correct density for both. Yes. Some other questions? So, thank you.